So thank you very much. Thank you very much for joining. I note that there are 530 participants, probably my biggest audience I've ever had, to be honest. So welcome to this presentation from my side. As Luis Manuel said, I will talk about the traceability from the new kilogram to our mass lab standards. So first of all, just a short recap about the new kilogram and how to understand the new kilogram. So the new kilogram, as you probably heard in previous presentations, is now based on the Planck's constant h. And this Planck's constant h has been realized or defined by two experiments, by the Keppel balance experiments as well as the XRCD experiment with the silicon sphere. So, as I said, in 2019, we redefined the kilogram with the Planck's constant, and the kilogram is not based anymore on a physical artifact. You can also see on this graph here below on the right side that those experiments, which have been carried out by those individual countries, have not been quite in agreement, and therefore a so-called consensus value has been defined from those experiments. The consensus value is kind of an average of all the experiments. So as of now, we have actually a correction value or a consensus value of -7 micrograms from the 1 kilogram IPK with an uncertainty of 20 micrograms. As soon, of course, all those experiments will be in agreement, there is no consensus value any longer necessary. So again, those experiments will continue. All those countries which are participating in those experiments will continue to do their research, and as soon they have an agreement, we will no longer need the consensus value. So talking about those two experiments, redefining the kilogram or defining the kilogram, first of all, we have the Keppel balance. The Keppel balance principle is a precise measurement method that relates mechanical power to electrical energy. It's quite challenging to explain, actually, if you're not really involved in those type of experiments, and if you're not a mass metrologist. Basically, it's working like a balance, right? The balance is equipped with a coil and with a magnet. The more current you flow through the coil, you can compensate the weight. You actually measure the current required to compensate the weight. So yes. So yeah, that's basically it. Yeah, you can measure the current, but basically in a Keppel balance like that, or in a balance like that, the parameters for the magnetic properties and the coil properties are not known, and therefore it's required to make an additional measurements, so-called dynamic phase measurements, to carry out or to detect the characteristics of the coil and the magnet. And with those principles, again, the static phase and the dynamic phase, electrical power can be compared to mechanical power, and we can therefore define the Planck's constants. On the left-hand side, you see such a Keppel balance. It's actually the Keppel balance installed at the National Metrology Institute in Switzerland. Very sophisticated Keppel balance which operates in vacuum. I'm mentioning now vacuum because I will later on explain you the challenges we have with vacuum. The second experiment was the Avogadro experiment, also called the XRCD experiment. It's basically the foundation determining the mass of substances based on the number of atoms. So we actually count the number of atoms which include in a 1 kilogram of mass. So you've probably already, or most of you, seen this silicon sphere already. It's a really kind of remarkable piece of object. It's very, very precious. I heard that the worth, the value of such a sphere is more than $1 million US, and it's actually, as a matter of fact, the roundest object on Earth. There's a lot of process steps involved to redefine the kilogram based on this Avogadro experiment. So of course you have to first manufacture the SI crystal, then the lattice parameter have to be measured. The volume of the sphere has to be measured very accurately with a laser interferometer, and the mass of the oxide layer is also very relevant to define the mass. And at the end, of course, you also require a vacuum mass comparator to be able to determine the mass of such a silicon sphere. Now, I want to talk about the traceability now. Since we redefined the kilogram, as mentioned, we have the Planck's constants as definition for the kilogram. So the number you see there is actually the definition of the kilogram. So this Planck's constants is fed into the basically fed into those experiments, and out of those we are able to create a weight. Basically, as I mentioned before, as those experiments are not in agreement, we have defined, or the NMIs have defined or come into agreement with a so-called consensus value. But from then on, the dissemination or the subdivision of mass or the traceability of mass is happening the same way as we have done it so far, right? So national prototypes will be being traceable to the consensus value. Primary standards will be traceable to national prototypes, and other weights then will be traceable to primary standards. So it's really like a comparison required. It's always a one-to-one comparison between a reference object and the measured object to fulfill or to carry out the traceability of mass. And of course, those masses will at the end then be used to calibrate or verify scales and balances. So for each of those steps in the traceability chain, mass comparators are required. So especially when those objects are coming out of those experiments, they are basically or mostly measured on vacuum mass comparators or constant pressure vacuum mass comparators. And then for other steps in the value chain, which requires not very high or lower, let's say lower uncertainties, other mass comparators will be used for that traceability chain. So there's different and various types of mass comparators fulfilling the needs for the calibration work. At the end here, you probably see this is a manual mass comparator, so the weights are actually loaded manually on the weighing pan to compare weights or to carry out the calibration. And on the left-hand side, you see very, very high accuracy mass comparators, even operating in constant pressure to achieve utmost accuracy because it's required. You can see the traceability chain as a pyramid. At the top of the pyramid, you require the most and best accuracy measurements to secure a certain level of uncertainty. So the challenge we have, actually, I mentioned it before. Both of the experiments, actually, the Keeble balance as well as the Avogadro experiment, are carried out in vacuum. And the vacuum has, of course, its benefits. So why do we actually measure in vacuum? Vacuum eliminates the buoyancy effects. So if we measure in vacuum, there is no buoyant to be seen on the measured object, and especially when comparing two artifacts or two objects with different densities, there can be a big influence of this buoyancy effect. If we eliminate the air, or if we remove the air, we don't have any buoyancy and air effect anymore, and we can measure very, very precisely. Considering that stainless steel has a totally different density than the silicon sphere, so therefore best measurements are performed in the vacuum environment. Also, platinum iridium versus stainless steel. Platinum has a very high density. All of you which have seen a national prototype before, the platinum weight is only 39 millimeters times 39 millimeters large. So we're actually comparing two different volumes against each other, and therefore elimination of buoyancy is really crucial. Also, in a vacuum chamber or constant pressure chamber, we can completely eliminate the air density change we have because of the weather, right? We cannot control the air pressure. Air pressure is given by the weather, and if we can put a mass comparator or a balance into a vacuum chamber or constant pressure chamber, we don't have any influences of the air density change. So we can create also better accuracy and precision. So when we measure, so when those objects are moved from the experiments to a mass comparator, we have to make sure that they remain in vacuum. Because if we move the weights from vacuum to the air, we have some issues coming along with it. So first of all, when we place a weight into the vacuum, the water layer, the surface layer evaporates, and this surface layer is actually very useful because it works kind of like a protection layer for the weight. So what happens to a weight when we move it from the vacuum mass comparator to the air? It will actually be contaminated by hydrocarbons and other molecules. So basically said, when we transfer weights from vacuum to air, we actually will gain mass. And this is something we want to avoid, right? So how is this done? So for the mass comparator, vacuum mass comparator developed actually for the redefinition of the kilogram, we've developed so-called storage and transport vessels. And so an object coming from the Kibble balance or Avogadro experiment can be put into a transport vessel within this experiment. So those transport vessels are in vacuum, and that they can be transferred to the vacuum mass comparator directly without ever exposing it to air. Especially when all the experiments were made to redefine the kilogram, those observations had to be very carefully made. So what happens to a weight when we move it from the experiment to air? I have a short video I would like to show you how such a transfer happens from an experiment to a vacuum mass comparator. So we have a vacuum, just going back to the video just to explain you the principle of this mass comparator. So we have on one side a vacuum chamber where we have the mass comparator built in, and on the other side we have a so-called load lock system. So this load lock system can be put into air and put into vacuum. It's like a sludge where we can operate the weights. So first of all, coming from the experiment, the weights are under vacuum inside of this storage and transport vessel, and we place it into this so-called load lock device manually. I hope you have a good visibility of the video. Then you can interlock the load lock or the transport vessel and connect add the connection piece to it. The next step would be we will actually prepare a so-called load lock hand to be able to then lift the weight later on into the vacuum chamber. We will close the door of this load lock device, and the next step is we will actually create vacuum in this load lock device. So there is vacuum inside of this transport and storage vessel and in the load lock. So we then can lift up actually the lid of the transport vessel, and you can see now the sphere and the object displaced. Now you can transfer the weight, or the operator can transfer the weight from the load lock device or from the storage container, transport container, to the mass comparator. This is actually done manually, so the weights will be moved from the load lock to the vacuum mass comparator. Of course, first of all, a gate valve has to be opened, and then the weights can be deployed very slowly onto the mass comparator's turntable. So all those weights there sit in vacuum, and this turntable rotates fully automatically and is able to load objects then onto the wing pan. You can actually see here in the video a sphere which is loaded onto the wing pan of a vacuum mass comparator, which has a readability of 0.1 microgram. As a matter of fact, it's the most accurate mass comparator, most accurate balance in the world, achieving uncertainties or repeatabilities of around 0.3, 0.5 micrograms. Good. So I told you now about the vacuum transfer. So we have to make sure the objects are transferred or remained in vacuum. But now at some point we have to go to the air atmosphere, right? And I mentioned before, when we move to air, eventually the surface of weights will be contaminated with molecules and hydrocarbons. And we need to make sure that this cannot be avoided, right? This cannot be avoided, and we have to make sure in which amount the weights are actually getting heavier. So this is done with so-called sorption artifacts. You see a picture on the right-hand side. Sorption artifacts are kind of disc weights, which basically are added up to 1 kilogram. So it's also 1 kilogram of mass with the same material, but with a much larger surface. So we can actually better detect or analyze what does happen with the surface of a 1 kilogram mass piece when we transfer it into the air. So this change of mass has been evaluated during the redefinition of the kilogram when all those experiments happened until 2019 and before, and actually also beyond. So the NMIs actually do know how much mass is gained on the weights when they transfer it into air, and this mass change or mass gain will actually taken into the consideration for the uncertainty calculation. So the mass change can vary up to 6 micrograms per weight if I transfer it from vacuum to air. And this can actually be cumulated. So if you transfer it many times, the weight actually could eventually increase. So there is a nice paper actually explaining all those investigations which were made at that time. So how much mass gain was done when transferring from vacuum to air. So now how is the traceability established from this weight, which has been transferred now from vacuum to air, to our other weights, to our other reference weights, to our other nominal weights? So this is a principle we call the dissemination or subdivision principle, and it's also done on mass comparators. Basically, mass comparators always compare the same nominal weights against each other. So 1 kilogram will be compared against 1 kilogram, 500 gram against 500 grams. So how can we disseminate from 1 kilogram down to other nominal values if we only have those mass comparators which can only compare two masses against each other? So we need to carry out the so-called subdivision dissemination principle. So on an automatic mass comparator, which you see here in this picture, it actually happens like that. You compare this 1 kilogram versus a combination of weights. So you have disc weights as a guiding or a supporting weight. So 200 gram plus 100 gram and another 500 gram on top equals up to 1 kilogram. So this 500 gram weight now can be transferred to the next step of measurement. So this is the first measurement. The second measurement will also include then a 500 gram measurement against all of the disc weights again. So this can be done with various groups. So the next step again would be then comparing a 200 gram weight disc against the 200 gram weight disc and so on. So a lot of groups are necessary. Actually, up to 8 groups of measurements are necessary to disseminate from 1 kilogram to 100 gram. And of course, there are various different kinds of dissemination methods possible. Yeah, why do we need to stack weights like this? Because it's because of the design of those automatic mass comparators. So weights cannot be placed next to each other, and therefore we need to stack the weights. So on a vacuum mass comparator, on an automatic mass comparator, like you see on the picture here, weights have to be stacked like that. So, but there are other mass comparators available in the market where a dissemination can be done directly by placing weights next to each other. For example, a robot system is able to do that, or other automatic comparators which have a large surface area, like you see on the picture here up right. So several weights can be placed next to each other for the dissemination. So the dissemination scheme or principle looks a bit different because we can combine, or we can place weights next to each other. The first group of this subdivision would then be a 1 kilogram versus two 500 gram weights placed next to each other onto the weighing pan. And then we will take 500 gram weight here to the second measurement, and the check standard here to the second measurement. So those weights here will be compared to against each other. Third group, then of course 500 gram versus 200, 100, 200 gram, and so on. So it also requires up to, I would say, 8 to 10 groups of measurements to do this. The advantage of a robotic mass comparator is that a so-called dissemination can be done fully automatically. Therefore, there is no need of unloading and reloading weights for each group, which you have to do on the left-hand side, by the way. So this can be done fully automatically. The advantage of automatic comparators, because we are measuring inside of a weighing chamber, is the best possible uncertainty we achieve like that. So that again, the turntable sits in a closed weighing chamber, doors will not be open and closed during the process, and therefore, like this, we achieved best possible uncertainties. With a robotic mass comparator, there is always an opening and door included in this process steps, right? So the robot system will bring a weight, the door opens, the weight will be deployed on the weighing pan, and this of course creates a little bit of instability within the weighing chamber, and therefore we will not be able to achieve the same level of uncertainties as we do them on an automatic mass comparator. So yes. So what about the future? This is probably my last picture I want to show. So how does the dissemination in the future look like? And this is actually a discussion which is going on at the moment. There is a lot of projects actually at the moment going on worldwide for the development of so-called tabletop Kibble balances. So that those are Kibble balances not at the NMI level, but rather than other nominal values or lower uncertainties. So who knows? Maybe in the future, Kibble balances will be able to calibrate weights at any nominal value. So yeah. So actually, the first let's say tabletop Kibble balance, which I know was installed in the US at the moment, and it's they are trying to. It's not part of their quality system as of yet, so they're still testing this type of Kibble balance at the moment at that facility. But yeah, maybe that could be the future, and this would be the end of my presentation, and I would be now open. Actually, I have one more slide, the conclusions. So my conclusion is vacuum mass comparators play a really crucial role in the redefinition of the kilogram because they were able to achieve the best possible uncertainties. And thanks to the vacuum to air experiments which have been done over the last couple of years, the NMIs or everybody who's doing research on the redefinition of the kilograms are aware of the mass change when transferring from vacuum to air. Best uncertainties are achieved in vacuum and constant pressure. And the dissemination and subdivision methods can be achieved on automatic and robotic comparators with lowest uncertainties. and the robotic mass comparators allow a fully automatic dissemination of weights or a weight set. Okay, so this would be the end of my presentation.